In this problem, it looks like we've got several situations of some before and after some change with a loop of wire and a magnetic field. And we want to know, is there any induced current? And if so, which direction is the induced current? And to figure this out, what's the main idea here? What sort of thing causes induced current in a loop of wire like this? Or what has to be happening to make induced current happen?
Electron flow.
Well, the electron flow is what the current is, but what has to be going on with the magnetic effects to make that happen?
Does there have to be a magnetic field?
There's got to be some sort of magnetic field, and also, more importantly, the magnetic effect has to be changing. Merely the presence of a magnetic field doesn't cause current to flow. But if there's some sort of change happening with the magnetic field in specific ways, then that does cause current to flow. And we call that induced current. And have you seen the idea of magnetic flux?
Yeah.
Yeah.
That's the main idea we're going to need to work with here. Magnetic flux, let's start with that. Usually written as a capital phi. How do we define magnetic flux in the first place? What is meant by flux?
Change in angle or area, or like the field that goes through some sort of like area.
Yeah, or rather that would be what the change in flux is. Flux itself is just defined as those three things: the area, the magnetic field, and the cosine of the angle. So area times magnetic field times cosine of the angle. And we're going to define the angle in terms of the normal vector in the same way that we were defining angle with refraction and reflection. And conceptually, what the magnetic flux means is to what extent is the magnetic field lines going through the interior of the loop. So for instance, if you have, let's say you've got a loop of wire, I'm going to try drawing this in 3D. Let's say you've got a loop of wire that's perpendicular to the plane of the screen. So like this edge is closer to you, this edge is further from you. That might make it a little more clear, something like that. And let's say we have magnetic field that is pointing to the right. Maybe this magnetic field is caused by a large bar magnet, or maybe it's caused by a current flowing in another wire somewhere else. But let's say we just got magnetic field pointing to the right everywhere. In that case, would you say that the magnetic field lines are passing through the interior of the loop?
Yes.
Yeah. So we would say this situation includes a large magnetic flux. Whereas if we take the exact same loop, but let's say the magnetic field is upwards, would you say that these field lines are passing through the loop?
No, because they're parallel, right? And then we have like...
Yeah, they're just skimming along the surface. So this would be a situation where the flux is 0. And note that all that changed there was the angle. We didn't change the area, we didn't change the magnetic field, we just changed the angle. And the way we describe the angle here, it's tempting to want to measure the angle between the magnetic field vector and the surface, specifically this surface here, the interior of the loop. But the problem is it turns out to be mathematically very inconvenient to try and define an angle between a surface and a vector. But it's very easy to create a perpendicular to a surface. So typically what we do in these cases is we take the surface, the interior of the loop, and we create a vector that's perpendicular to it. And we call this the normal vector. And this is the same idea as the normal line we drew in when we were dealing with reflection and refraction. So this normal vector essentially represents the orientation of the surface. It's perpendicular to the surface, but no matter which direction the surface is oriented, the normal vector is unique. Well, not entirely unique. There's really two choices for the normal vector. For this surface, we could have a normal vector going to the left or to the right. Either one would work. But what's the angle between the normal vector and the magnetic field?
So in this case that you drew would be 90.
Yeah, the way it's depicted here, this is a right angle, 90 degrees. And we want the result to be 0. We want the flux to be 0 here because a field line that's just skimming along the surface is not really going through the loop. So what trigonometric function is 0 when the angle is a right angle?
Oh, sine.
Sine of 90 is 1, so that would be very large.
Cosine.
But yeah, cosine will work well here. And this is exactly why we use cosine in the formula for flux. That way, cosine, if the field is perpendicular to the normal vector, we get 90 degrees. So cosine of 90 degrees is 0, meaning no flux at all. And that's what theta means here. Theta is always representing the angle between the normal vector to the surface and the magnetic field. So if you have the magnetic field skimming along the surface, that's perpendicular to the normal vector. So theta is 90 and cosine of 90 is 0, no flux at all. Whereas if you have the magnetic field lines at some other vector or some other direction, like let's say the magnetic field lines are on some diagonal. Let's say the field lines are about like this direction. So the magnetic field lines continuing through the loop, something like this. If you have magnetic field lines that look like this, now they're not perpendicular to the normal vector, so cosine is not 0, but they're also not parallel to the normal vector, so cosine is not as big as it could be. Instead, we just have this angle, and specifically the angle we're talking about is the angle between the magnetic field vector and the normal vector. So that angle is the theta described in the equation. So the actual magnetic flux would be the area of the loop times the magnetic field magnitude times cosine of the angle between them. And ultimately, that gives you the component of the magnetic field in the direction perpendicular to the loop, in the sense that the magnetic field vectors could be thought of as a parallel component and a perpendicular component. All we really care about is the component parallel to the normal vector, that is going through the loop. The component that's perpendicular to the normal vector is not really going through the loop, so it's ignored. But ultimately, that just turns into AB cosine theta. Any questions on that so far?
No.
And what angle would lead to cosine being the largest?
180.
Yeah. Well, actually, if it's 180, if they're exact opposite directions, let's say you have field lines that are pointing exactly the opposite direction to the normal vector. So looking like this. It's not going to be 0 in this case. This would be, or do you mean as the angle? Yeah, cosine is going to be largest when the angle is 0. In this case, if the field lines are pointing in the direction exactly opposite to the normal vector, we would describe that angle as 180 degrees. And what's cosine of 180 degrees? Yeah, cosine of 180 degrees is -1. So that would mean you'd end up with a negative value for magnetic flux. Mathematically, that works, but it tends to be kind of confusing in terms of trying to understand what's going on conceptually. So typically what I would do there, if you've got a magnetic field going in a direction that's opposite to the normal vector, I would just use the other normal vector. Because remember, you can use the normal vector in either direction as long as it's perpendicular to the surface. So I would just use a normal vector that's pointing to the right instead. generally you have two options for choice of normal vector. So I would just choose the one that most closely agrees with the existing magnetic field. Not mathematically necessary, but it makes it easier to understand conceptually what's going on. Because it's a lot easier to figure out, is something increasing or decreasing if that something is a positive value. So in that case, the angle would be 0, cosine of 0 is 1, so you get a large amount of flux. Flux would just be A times B, area times magnetic field. Any other questions on that so far? And if you take a look at the units of measurement for magnetic flux, have you seen units of measurement for magnetic field yet?
Is it Tesla?
Yeah, magnetic field is measured in units of Teslas. And what's area measured in?
Meters squared.
Right. So magnetic flux has units of meters squared Teslas. If you simplify that though, if you substitute in the actual meaning of Teslas and simplify, you end up with equivalent units to volts times seconds. And this ties into the reason why this influences electrical circuits. That magnetic flux isn't volts, but it's volts times seconds. How could you turn that into volts?
You just divide by seconds.
Right. In other words, divide by time. So flux itself doesn't directly influence the electrical circuit. Like just having a value of flux doesn't do anything. But if flux is changing as time passes, if we look at the derivative of flux, d flux over dt, wrong symbol. Derivative of flux, you get volts times seconds in the numerator and seconds in the denominator. Divide those and you end up with volts. So that means the derivative of flux is a voltage. What this means physically is that if the flux is changing, it doesn't really matter whether there's flux or not. What matters is whether the flux is changing. If the flux through this loop is in the process of changing as time passes, that means this loop will experience voltage even if there's no battery involved. You get an extra bit of voltage. Well, if there's no battery, you get some voltage because of the changing flux. If there is a battery, you get some extra voltage beyond that because of the changing flux. And the faster flux is changing, the more voltage you get. Sorry, what was that? And if you think back to what you saw about circuits in 7b, what does voltage do? If you've got a loop of wire and you've got a voltage difference, what would you expect that to cause to happen? Like if we go back to a circuit diagram, let's say you have a loop of wire with a resistor. And typically, what would we expect to be providing voltage in a circuit like this?
Battery?
Right. So let's say there's a battery here. The battery provides a voltage boost. What happens to a resistor if it has voltage applied to it? If there's a difference in voltage? We can sort of treat voltage as the electrical push or electrical pressure, but what's that causing to happen? What would you expect to happen if you take a battery and let's say a light bulb or something and wire them up like this?
It would light up and the voltage would decrease.
In the sense that there's a difference in voltage across the resistor, yeah. The battery is still providing the same voltage increase, but the resistor is now going to get a voltage decrease to match. And what's the usual formula for delta voltage of a resistor? Anytime you're dealing with, negative IR. So the fact that there's voltage difference, in this case caused by the battery, that voltage difference causes current to flow. So you're going to get current flowing from the high voltage zone towards the low voltage zone. So the presence of a voltage difference in a loop of wire, as long as it has some resistance, causes current to flow. And the amount of current is going to be delta V over R, at least in terms of absolute value. The negative sign ultimately just refers to the direction current is flowing. But the amount of current is the voltage difference divided by the resistance. However, if you're dealing with magnetic effects, the magnetic flux changing, the process of the change in magnetic flux as time passes creates extra voltage, which means if there's extra voltage, you could get current flowing in this loop of wire even if there's no battery. Even without any battery at all, as long as there's a complete loop. The changing flux creates extra voltage. That extra voltage, which we call the induced voltage divided by resistance, tells you the current that's going to flow in that loop, the induced current, the current caused by the changing magnetic effect. And this is the foundation of any sort of wireless power transmission. You use a changing magnetic field to cause current to flow in a loop even without batteries in it. Anytime you want two sections of wire to influence each other without physically touching, this is generally how it's done. You use one loop of wire to create a magnetic field that changes as time passes. And then the other loop of wire experiences induced current and induced voltage because of the changing magnetic flux. Any questions on that so far?
Yeah, I have a question. So if the change in the flux is the voltage, but current is dependent on change in voltage, I'm confused how the current if voltage is not changing through the loop.
It's really more that the derivative of flux tells you a delta voltage for the whole loop. If you go back to 7b, do you remember the loop rule for 7b for circuits?
That like the voltage is if you start at one point and end there, the change is zero.
Yeah, for any loop, starting and ending at the same point, the sum of the changes in voltage is zero, which would suggest, for instance, that if you have a loop with just a resistor, that resistor is getting no voltage difference, so it gets no current. It turns out the loop rule as written here is only valid if there's no magnetic effects. The idea of flux here, this d flux dt equals delta V for the whole loop, this is effectively a correction to the loop rule, a slight adjustment. The loop rule, if we want to be more accurate and include magnetic effects, it's not that the sum of the voltages in the loop equals zero, it's that the sum of the delta voltages in the loop equals d flux over dt. Strictly speaking, that should be negative to account for direction. But the flux, the rate of change in flux is essentially an extra term in the loop rule. That you get this extra voltage for the loop that depends on how fast the flux is changing. And note that if the flux is not changing, regardless of whether there's flux present or not, as long as the flux is not changing, what's the derivative of a value that doesn't change?
It's just constant or zero.
Right, derivative of any constant would be zero. So if the flux is constant, then this is just zero. And we get the usual loop rule we saw back in 7b. So 7b, all the stuff we were doing with circuits assumed that there's no changing magnetic flux. In fact, we were generally just assuming there were no magnetic fields at all. But the important thing isn't whether there's a magnetic field. The important thing is whether the magnetic flux is in the process of changing. If the flux is not changing, no matter how strong the flux is or isn't, if the flux is not changing, then you get no induced voltage. So the loop rule, as usual, still stands. The sum of all the delta voltages is zero. But if there is flux in the process of changing, then the voltages don't add up to zero, they add up to the derivative of flux instead. And the negative sign here just represents direction. Any questions on that so far?
Yeah, I have one more question. So since we have a change in voltage, would that mean there's also an electric field present within the loop?
I don't think so. I think in this case, the voltage is the result of the changing flux or the changing magnetic effect rather than the result of an electric field.
So if we were to put like a charge in the loop, like a positive charge, then would the change in voltage have to like realign to the like in relation to the positive charge? If that makes sense.
I'm not quite sure what you're asking there. Do you mean, are you treating this positive charge as a source charge or a test charge?
As a source charge.
So we're looking at the effect it has on the loop of wire?
Yeah.
In that case, I don't think it would have any effect because the positive charge, if it's just staying still, it's only creating an electric field. An electric field won't influence the wire directly because it's not the wire is not charged. The wire just has current flowing within it. I guess the presence of the source charge, which also creates an electric field, could implement its own voltage, which could influence the current. But I don't think that would really play a role in the flux. The flux is just about the magnetic field itself.
Okay.
And what else? Also, I mentioned if the flux is not changing, the derivative is 0, so you get no extra voltage. If the flux is changing, you get an amount of extra voltage, or delta voltage technically, that is equal to the rate of change in flux. So if the flux is changing very slowly, you get a little bit of voltage. If it's changing very quickly, you get a lot of voltage. And that voltage typically causes current to flow in the loop. So that's what we call induced current. If you want to check if there's any induced current at all, you would need to check, is the flux in the process of changing? For example, in the first example or first situation described here, it looks like we've got a bar magnet, which creates a magnetic field. And we've got a loop of wire. And all we're doing is tilting the wire, or we're rotating the loop of wire. What can you say about the magnetic field caused by this bar magnet, at least in the region of the loop itself? In this region, which direction would you expect the magnetic field to be pointing?
It goes to the right, but I don't think it passes through the loop, does it?
Well, the magnetic field, we have a north end here, right? The magnetic field be pointing towards or away from the north side?
Away.
It's away.
Right.
Yeah. So we should expect the magnetic field in this region of space to look like this.
Oh, okay.
So outward from the negative side and then inwards towards the south, or sorry, outwards from the north side and inwards towards the south side. But all we really need to care about is the immediate vicinity of the loop itself. And yeah, is that actually passing through the loop?
It should not be passing through the loop.
Right. So at this instant in time, flux is 0. And note that that doesn't tell you whether there's induced current or not, because induced current isn't about is there flux or not. It's about is the flux in the process of changing or not. So we need to check both before and after. We can say the initial flux is 0, whereas for the final flux, we haven't changed the magnet, so we still have the same magnetic field pointing right to left. Same magnetic field as before, but we have rotated the loop of wire. And it's kind of difficult to see in this diagram. Let me see if I can draw that a little more clearly. It says the point marked A ends up above the plane of the page. So we have changed it from a loop that's flat within the page, and we've rotated it something like this. I guess I should probably draw those the same size since they're supposed to be the same loop. And we've specifically rotated it so that point on that was originally on the left side of the loop is now on the edge close to the viewer. So something like that. And would that imply that the flux has changed?
Yes, because you have magnetic field lines going through it.
Yeah, conceptually, we can say originally we didn't have any field lines going through the surface. They were just skimming along the surface. But now the field lines are passing through the surface. In fact, they're passing through the surface perpendicular to the surface itself. So we have a very large amount of flux. There's definitely a change in flux here. So we should expect induced current. We should expect induced voltage, which causes induced current to flow. Any questions on that so far? And to determine direction, we usually write this as derivative of flux equals negative delta voltage. The negative signifying that the direction of the voltage difference is opposite to the direction of the change in flux. So if we want to associate a direction with this change in flux, usually we associate flux with the direction of the normal vector. And as usual, we have two options for normal vector because there's two directions perpendicular to the surface. Before both of those, actually in the before situation, what would be the two options for normal vector?
You could have it into the page or out of the page.
Right. And note that both of those are equally perpendicular to the magnetic field. So there's not really a preference for either one. But if we take a look at after, what are our options for normal vector?
To the left or to the right?
Yeah, those would both be perpendicular to the surface. And we want to choose the one, again, mathematically, either one of them will work. But it's going to be probably the easiest to make sense of it conceptually if we choose the one that most closely agrees with the magnetic field. So I would choose the one to the left. Let's use to the left as our final normal vector. So in the end, we're assuming the normal vector is pointing to the left. If you rewind time to get back to the original, which direction is the normal vector? If you imagine this rotating.
Should be into the page.
Yeah, because there's, again, thinking of this red dot as originally on the left and rotating so it's now on the side of the loop closest to the viewer. If we backtrack, if we put that back, the normal vector that was pointing to the left in the end should have been pointing inwards in the beginning. So we'll treat the original normal vector as inwards. And that means we can think of that as the direction of the flux. Inwards at the beginning and to the left at the end. And in this situation, is the flux overall increasing or decreasing?
It's
increasing.
Yeah, we've got an increasing flux. And if we treat the flux as the direction of the normal vector, so let's say at the beginning, the flux is treated as inwards, and it's 0, but it's going to be inwards as soon as it starts to grow. If it's inwards and increasing, would you say that the change in flux is inwards or outwards?
inwards.
Yeah, change in flux is in the inwards direction. Because if it's an inwards vector and it's increasing, then the change is more and more inwards. So we've got an inwards change in flux. And the derivative of flux is supposed to be the opposite of the change in voltage. This negative sign means take the opposite of that direction. So the change in flux is going to be inwards, but the induced effect is going to be in the opposite direction. In general, the induced effect is in a direction, or is associated with a direction opposite to the change in flux. That's what this negative sign signifies. So the induced effect is outwards. But how can you associate outwards a linear direction with a current flowing in a circular pattern in this loop? How do we usually tie together a linear direction versus a rotational direction?
Right-hand rule number one.
Is that the first right-hand rule?
I think I would say probably right-hand rule number one should work. In particular, the variation involving a loop of wire. If you point your thumb in the direction of the magnetic effect, then the curl of your finger tells you the direction of current in the wire. And we want the induced effect to be outwards. So point your thumb in the direction pointing out of your screen, so towards yourself, and the curl of your fingers should tell you the direction current's going to flow. So which direction is that going to be? If you point your right thumb outwards from the screen, towards yourself, towards the viewer.
Counterclockwise.
Yeah, that should be current flowing counterclockwise. So we can say that in this situation, as soon as the loop starts to rotate, we're going to get current flowing counterclockwise. But that's only going to last for the period of time during which the loop is rotating. As soon as you stop rotating the loop, there's no more change in flux, so the current would immediately stop. Any questions on that example so far?
Wait, yeah, just to recap. So the change in flux is inwards because it gets larger and it starts inwards. But why is the induced effect outwards?
Well, technically the flux starts at 0, but as soon as the loop starts rotating, you get an inwards flux that gets more and more inwards. But the idea is of this negative sign in the, I think this is called, is it Lenz's law or Faraday's law? If I understand correctly, one of them is the equation and the other one is explaining what the negative sign is. Sorry, what was that?
I was going to say, I think it's Lenz's law.
Okay. So that tells you that the derivative of the flux is negative change in voltage, or negative induced voltage difference. So the negative sign is ultimately telling you that the induced effect, the induced electrical effect, voltage in this case, is in a direction opposite to the change in flux. So if the change in flux is inwards, we should expect the induced effect to be outwards. And then you can use the right-hand rule to translate that into an actual direction of current flow. In this case, counterclockwise. Any other questions on that example so far? Then let's take a look at the second example. In this case, we're not moving the loop at all. The loop is just staying still. But what is changing? From before to after.
It's the magnetic field.
Yeah, and yes, because we're adjusting the amount of current in each wire. We're going from weak current in the left wire to strong current in the right wire to strong current in the left wire, weak current in the right wire. So that does change the magnetic field in this in-between region. And to figure out which direction we're talking about, what would be the magnetic field if we take a look at each of these source wires individually? Because it looks like we're treating these source wires, these long straight wires, as the source of the magnetic field. And then the loop of wire in the middle, which is unpowered, is experiencing magnetic flux as a result. So what would be the magnetic field from the left wire in the interior region?
It would be clockwise. Oh, wait, in the interior region?
Yeah, that is on the right side of the left wire. You can use the right-hand rule for
out of Would it be coming out of the page?
From the left
on the
wire?
right side. Yeah.
I think that's going to be inwards, actually. Because if you
Sorry,
put the thumb in the direction, sorry, go ahead.
Yeah, I used my left hand instead of my right hand.
Yeah, that'll do it.
So I got them mixed up.
Okay, yeah, right hand rule, point your thumb in the direction of current and the curl of your fingers should tell you the direction of the magnetic field. So that suggests on the right side, we've got an inwards magnetic field. And then on the left side, we've got an outwards magnetic field. And as usual, the closer you are to the wire, the stronger that'll be, and the further you are, the weaker it'll be. All we really care about, though, is the region of the region within the loop itself. That's to the right of this wire, so we can expect an inwards magnetic field. But it's also to the left of the right wire. So what would be the magnetic field on the left side of the right wire?
Out of the page?
Right, that'll be outwards. And would it be stronger or weaker or the same?
Stronger.
Yeah. Because we got twice as much current, that should induce or should create twice as much magnetic field. So if we've got a weak inwards field plus a strong outwards field, what's the overall magnetic field there?
Outwards.
Yeah. In this region, the only region we care about, the interior of the loop, we've got an outwards magnetic field. So in this region, we've got an outwards magnetic field. And how does that change in the final situation, the after situation? If we switch it so that the left wire is now the stronger current and the right wire is now the weaker current. Would the inwards or outwards effect win out here?
Sorry, there's like a fire.
Sorry, what was that?
I think there's a fire alarm going off at campus.
Oh, you better get out of there then.
Yeah. If we flip it, then it should be going into the page.
Yeah. So that'll be in the inwards direction. Which means that overall there's now a change to flux. Even if it looks like it's going to be the same strength. We start with some amount of flux, we end with the same magnitude of flux, but it's now in the opposite direction. So if we look at this in terms of directionality, the initial flux is outwards. The final flux is inwards. So which direction is the change? If you've got a value that's originally pointing outwards, but it changes to pointing inwards, what's the direction of the overall change there?
Into the page direction? I mean, wait, hold on. Mm-hmm. Yeah, into the page direction.
Yeah, that should be the inwards direction. So in this case, the delta flux is in the inwards direction. And again, according to Lenz's law, the negative sign here, we should expect the induced effect to be in the opposite direction from that. So the induced voltage, the induced effects overall is in the outwards direction. And again, we can use the right hand rule in the same way. Point your thumb in the outwards direction and curl the fingers of your right hand. And the curl of the fingers should tell you the direction current is flowing. In fact, it looks like this will be the same as the previous one, since we have the same outwards induced effect. So that'll be counterclockwise current. Any questions on that so far? And then for the third one, there's definitely a magnetic field from the source wire, and that magnetic field is going to be in which direction?
It's going to be out of the page.
Yeah, you should have an outwards magnetic field. And the magnetic field isn't changing, but what is changing here?
The area.
Right. And so what would you expect that to do to the flux?
Increase it.
Yeah. Initial flux is going to be, let's say, small and outwards. And then the final flux is large and outwards. So which direction is the change overall? Yeah. Delta flux. Sorry, what was that?
Increase and out of the page.
Yeah. So we'd say that the delta flux is in the outwards direction. And that means the induced effect, again, has to be opposite to that because of the negative sign in Lenz's law. So the induced effect is inwards. And again, you can use the right-hand rule for this. Point your thumb in the inwards direction, and the curl of your fingers will tell you the direction that current is flowing. So point your thumb in the inwards direction, and which direction is current going to be?
Clockwise.
Yeah. So we'll get current flowing in the clockwise direction. And again, that's only going to be flowing while the flux is in the process of changing. So while you're in the process of expanding the area, the current will flow. As soon as you stop changing the area, there's no further current flowing. The current just immediately stops. Any other questions on that or flux in general? And one other thing I want to mention, since the formula for flux involves these three things being multiplied together, area, magnetic field, and angle, if any one of those three things is changing, that could signify a change in flux and therefore an induced effect. If none of those are changing, or if maybe two of them are changing in ways that balance each other out, then there's no change in flux and therefore no induced current. So that's really what you want to check. Is any one of those changing? Any other questions or anything else you want to work on?
This is the first practice final, right? Can we do like question 1C?
Yeah, one moment. Is that on the other one?
It's on the same practice final that you're on.
Let me pull that up then.
It's the first question, number C, or part C.
Yeah. This one. Is that somewhere in here?
Oh, maybe I can like send it to you.
Yeah, I don't think it's in this one.
Okay. I'm gonna look for it.
So here you got two speakers and you start at point A and you're walking towards point B.
Yeah.
What do you know about what's going on at point A?
So at point A, you don't hear any sound. So
Right.
that means there's destructive interference.
Yeah.
And so it says when you go from A to B, it gets loud and then soft, which means that you kind of traveled a whole like period or like high.
We're going through a full cycle, yeah.
Yeah. And
so
then
you've got a destructive interference here and again at point B. So somewhere in between, you pass through a single location of constructive interference.
Yeah.
So let's mark that also, presumably exactly in, well, maybe not exactly in the middle, but somewhere in between. Somewhere in between, you happen to pass through a point of constructive interference. Okay. And what else do we know about this, or what are we trying to find?
We're trying to find the unknown distance d. So
okay.
Yeah.
And if we'll probably want to take a look at the total phase for both point A and point B. So let me pull up the total phase equation. There it is. So for the total phase difference equation, the 2 pi t delta f, actually, is there any difference in frequencies between these?
No, because they have destructive interference, right? So that means they should be the same.
Well, it's more to the point that tells us that they're both playing, in part B, it's saying they're both playing the same tone, 425 hertz. In part A, they were playing slightly different frequencies, which is why we got beats. But in part B, we've corrected that, and there's no more difference in frequency. So since there's no difference in frequency, they're both playing the same frequency, and they're both arriving at your ears at the same time, this term is going to be 0. There's no difference in the time term. And there's also no difference in wavelength then, so we can factor out lambda from this equation. So we can ignore the time term entirely, and the lambda term can be factored out of the delta. So 2 pi delta x over lambda. However, at location A, what do we know about the difference in path length? If we compare the distance from speaker 1 to location A versus from speaker 2 to location A, what's the difference between those two distances?
0, because it's the same.
Right. So at location A, delta x is 0. Which means this entire first term is gone, because negative 2 pi times 0 over any wavelength is 0. So all that's left is the phase difference, if there is any. But also, we know point A is destructive. So what does that tell us about delta little phi?
It has to be, I forgot what it is, but it's like one of the multiples of pi that indicates like a full like cycle, right?
Well, if it was a full cycle offset, like let's say you've got 2 waves and they're a full cycle offset, this crest now matches up with the next crest. So that would be constructive. So to get destructive, what do you have to have the offset be?
Oh, it has to be half a cycle.
Exactly. And in radians, what would that be?
It's just pi, right?
Right. So we can assume that delta little phi must be pi. And technically, it could be any odd multiple of pi, but just using 1 pi is going to make things easier to work with. So let's say at this location, the delta phase shift is pi. And that's really the important information from point A, that if we didn't know that point A was destructive, we wouldn't have been able to find the delta phase shift. As you walk around, that phase shift difference should stay the same, because we're not modifying the speakers. We're just modifying where you are. So all that's going to change as you walk around is the delta x term. Any questions on point A so far?
No.
So let's take a look at point B. We still have no difference in the time term, but there is now a difference in path length. You've got a difference in how far the waves travel. So if you've got, let's say speaker 1 has a wave that travels this far, and speaker 2 has a wave that travels this far. So what's the difference in how far they travel?
Some distance like x. right?
It's actually already marked on the diagram. How much longer is one of these paths than the other?
Wait, they tell us?
Not as a number, but as a variable. Because we've got this distance, which is longer, and this distance, which is shorter. But how much longer is the longer distance?
Ooh, is it like one of the deltas minus another?
Not exactly. It's just this distance d marked in the diagram. And we don't know the numerical value of that, but the diagram already provides us with a variable for it. So we may as well use that variable. It might help to think of the distance from speaker 2 to point B as some unknown distance, let's say some length L. If the distance from speaker 2 to point B is length L, how would you describe the distance from speaker 1 to point B?
D plus L. Oh, and then the difference is just minus L, so then L cancels out, it's just D.
Yeah, exactly. We'd just be subtracting those. D plus L minus L, so delta X is just going to be D. Or negative D, depending on which order you subtract in. But the important thing is just to be consistent about the subtraction throughout the whole problem. So let's say we subtract and we get D as the difference in path length. Delta X is D, so that means this becomes negative 2 pi times D divided by wavelength plus delta little phi. And I guess since this kind of depends on which order we're subtracting in, we might want to think of this as having a plus or minus attached to it. But also, what do we know about the delta little phi?
It has to be pi.
Yeah. And then what about for the, do we know the wavelength here? Or can we find it?
It's, oh man, I don't remember the equation.
Or what other piece of information relates those?
Is frequency?
Frequency, because we know frequency, and we're trying to find wavelength. What does frequency times wavelength have to be?
Velocity.
Yeah. So if we put those together, frequency times wavelength equals velocity. Wavelength is just going to be speed over frequency. We have the frequency 425. Are we making any specific assumptions about the speed?
It's sound. So do we use 340 meters per second?
Yeah, I think that'll work. It's typically somewhere around 340, 345, somewhere around there. But yeah, let's say 340. And if it specifically states the speed for sound, you would use that. In this case, it doesn't seem to state any, so I would just state in your explanation, I'm assuming that the speed of sound is 340.
Okay.
So that means the wavelength would be 340 meters per second divided by 425 hertz. And what is that going to be? 340 over 425.
0.8.
0.8. That seems convenient. So 0.8, and the seconds and hertz, or 1 over seconds is the same as hertz, so those cancel out. We just get 0.8 meters. So that'll be the wavelength. And so we've got D as the unknown distance we're trying to find. We still also have delta capital phi, though, the difference in total phase. Is there any way we could find a value for delta total phase to use here?
Is it because it's destructive? You use the, I forgot, it's like something, you have like a fraction version of pi, right?
Not exactly a fraction of pi, a certain fraction of a whole cycle. Because if the offset is a whole number of cycles, you get constructive interference. If it's something in a half cycles, you get destructive interference. So what's one full cycle in radian measure?
Oh, constructive is 2n pi.
Right, because that's a whole number of cycles.
Destructive is going to be n plus 1 over 2 pi.
Yeah, because that's an odd number. Oh, wait, is that going to work?
Right?
I think what you want is 2n plus 1, because that'll give you an odd number.
Oh, yeah, the other version is n over 2 plus 1. Wait, no.
N plus 1 over 2.
The other version is n plus 1/2 times pi.
Yeah, times 2 pi.
Got them mixed up.
The important thing is it's got to be something and a half cycles, and a cycle is 2 pi. So something and a half cycles would just be an odd number of pi. But if we actually label out the delta total phase we're dealing with here, originally we were at a destructive interference location, and we were assuming that delta total phase was pi. And that came from just delta little phi is pi, so delta big phi is pi, because that's the only change, the only difference. If we move to the very next constructive point, what's the very next constructive value after 1 pi?
2 pi.
Right. So for this constructive spot, presumably delta total phase is 2 pi. This, I mean, constructive alone would just tell you it's some even multiple of pi, some whole number of cycles. But since it's immediately adjacent, it's the very next constructive point. It has to be the next even multiple of pi. And then if we keep going to get to the next destructive point, what's the next odd multiple of pi? The next something and a half cycles.
3 pi?
Yeah. So presumably this location has delta total phase being 3 pi. So you could fill in 3 pi for delta total phase and then solve for D. Or alternatively, since we don't really know the direction here, maybe you're going from pi to 2 pi to 3 pi, or maybe you're going from pi to 0 pi to negative 1 pi. So you could use either pi or negative pi for delta total phase. The important thing is you want a result that gives you a positive value for D.
Okay. So did we have to analyze point A, or did we just have to analyze point B?
We did need some information from point A. Specifically, point A got us information about the phase shift difference. If we didn't know point A was destructive, we wouldn't know that there's an offset between the two speakers.
Got it.
Any other questions on that one? Or anything else you want to work on?
Can we do question 4B?
Yeah, one moment. Pull that up. On the same one?
Yeah.
List? Okay, let me pull that one up. 4B with the 3 charges.
Yeah.
Okay. So what's going on in this one, or what are you trying to find?
We're trying to find the force experienced by charge B due to the other 2 charges. And we have to find the magnitude and direction. So I narrowed it down to, we're basically only using X components because it's horizontal vectors.
Yeah, we can treat this as one-dimensional. Did you find the charge of object C in the previous part?
I did, but I haven't checked my answer, so we can do that one too if we like.
Yeah, we might want to run through that one as well, just to make sure. What are we assuming about this situation in order to find charge A or charge C?
Because charge A doesn't experience a net force and charge B is a negative charge, that means charge C has to be positive.
Yeah, we can at least say it's going to be positive. And then we'll still need to figure out how strong that charge is also. But we know that its charge C is at least positive. And to figure out how much, if charge A is experiencing no net force, what do we know about the electric field at location A?
It has to be 0.
Right.
Like, you add them.
Yeah, because the only way to get a charged particle experiencing no electric force is if it's at a location with no electric field. So what might be useful here is to ignore charge A entirely. Instead of treating it as a charge, treat it as just an empty point in space. So ignoring charge A, let's just talk about location A. So A is just this empty point in space. And we want to assume that the electric field at location A is 0. Zero electric field. And in order to find the electric field, if we look at the contributions from charge B and charge C individually, charge B is a negative source charge. So it's going to create electric field at location A in which direction?
Sorry, can you repeat that?
Charge B is a negative source charge. So it's going to create electric field in what sort of direction?
Towards it.
Yeah, so at location A, that means to the right. So that would be the electric field contribution caused by B at location A. I'll call that E sub B. And in order to cancel that out, we need charge C to create electric field in which direction?
To the left.
Yeah, which we can achieve by having C be a positive charge, as you said before. So that takes care of the direction. But what do we want? What do we need to assume about the magnitudes of these two electric fields? If we want two vectors to add up to 0, they've got to have exact opposite directions, which they do. And what has to be true about their magnitudes, their sizes?
C has to have a greater magnitude because it's a greater distance.
Not the charges, but the electric field vectors themselves. What's the only way two vectors can add up to 0?
Oh, okay. They have to be the same.
Right, same magnitude. And yes, that does mean that C is going to have more charge to balance out the greater distance. But to figure out exactly how much charge, we can do that by setting the magnitudes equal to each other, the magnitudes of the electric field. So let's assume that magnitude of electric field B equals magnitude of electric field C. The directions are already known to be opposite. Let's assume the magnitudes are the same. And do you have a formula for magnitude of the electric field from a single point source charge like this?
KQ over R squared.
Yeah, so we can say K times QB over RB squared equals KQC over RC squared. K is the same on both sides, so we can cancel that out. And then how would we solve for the unknown charge?
We plug in the charge for B and then the...
Well, before even plugging in any numbers yet, just algebraically, how would you isolate QC in this equation?
Oh, you would take, you would multiply by RC squared.
Yeah, so charge C is charge B modified by RC squared over RB squared. And again, before we even plug in numbers, there's one more algebraic trick we can do here. Anytime you got something squared over something squared, if it's the same exponent on the numerator and denominator, you can combine that as just the fraction RC over RB squared. And what do we know about that ratio of distances?
It's 1 to 2, or no, it's a 3 to 1 ratio.
Yeah, because we're measuring from A to C and from A to B. So RC over RB is a 3 to 1 ratio, which means charge C is charge B times 3 over 1 squared. And what's 3 to 1 squared?
9.
Right. Charge C has to be 9 times as strong as charge B, at least in terms of absolute value, in order for this to work. Because it's 3 times as far away, it's got to be 9 times as much charge because of the squared on the R. And I would generally recommend working out things like this in terms of variables as much as possible, because you can often get useful insight like that, like the idea that, oh, 3 times as far away means 9 times as much charge. That might not have been as obvious if you had plugged in the numbers right away. So we can just take the charge of B and multiply by 9. That'll be the charge at C. And also, of course, make it positive instead of negative. So 6 times 9 would be 54. So charge C is positive 54 times 10 to the negative 9 coulombs. Any questions on that so far? And now that we know charge C, we can use that information to answer part B as well, where we're trying to find the force experienced by charge B due to the other 2 charges. Which means we're going to need to have to open up charge A again, instead of just treating it as an empty point in space. And now we had previously been treating B and C as the source charges and A as the test charge, in the sense where we were trying to figure out what the effect created by B and C was. But now we're kind of switching that around. We're saying B is experiencing a force from the other 2 charges. So we're treating B as the test object that's experiencing some sort of force, and A and C as the source charges that are creating that effect. So let's see what we can do with that, now that we know charge C. Since we're treating charge B as a test object, I would start this by pretending B is just this empty point in space. So ignoring charge B and just treating it as location B, this empty point in space. And what do charges A and C create there?
They create a net field to the left.
Yeah, in fact, it looks like they're both creating electric field to the left, yeah? Because A is a negative source charge, so it creates electric field towards itself. C is a positive test charge or positive source charge, so it creates electric field away from itself. And without even knowing how strong they are, they're both pointing to the left, so we get a very strong result to the left. Since B and C are both pointing to, or A and C are both creating electric field to the left. At location B. So let's see if we can find the total electric field there. Each one of those, EA and EC, is a field created by a point source charge. So we can use the usual formula KQ over R squared. So electric field is going to be KQA over R squared plus KQB or QC over RC squared. And in this case, we can just add those magnitudes together because both the vectors are in the exact same direction. They're parallel to each other, pointing in the same direction. So we can just add their magnitudes. I guess we should probably think of these as absolute values of charge, though, because we want the results to be in the same direction. And if we fill those in, and here we are actually looking for a number, so we may as well just fill in the numbers directly. What do we know about the R values? What would we use for those? That is, what's distance A and what's distance C?
Charge A is going to be over 100. Actually, can we just cancel out the extra zeros and just make it like 1 and then 2 in the denominator?
Well, we do want the actual value here.
Okay, so then
I would go ahead and fill in the value as written. Okay. Although K is going to be in terms of meters, coulombs, seconds, and kilograms. So I would convert the centimeters to meters in this case.
So 0.1?
Yeah. In the previous situation, we didn't need to because we were looking at a ratio of distances. So in the ratio, it doesn't really matter what units you're using as long as they're consistent because they'll cancel out anyway. But in this case, we do want an actual value. So it's a good idea to convert the distances to meters. So charge A divided by 0.1 meters squared plus K times charge C over 0.2 meters squared. And we can fill in the values for the charges as well. Charge A, and I'm going to ignore the negative sign because we're just looking at magnitude at the moment. We've already taken care of direction. 6 times 10 to the negative 9 coulombs. And then charge C, 54 times 10 to the negative 9 coulombs. Any questions on that so far? So also everything here has a K in it, so we may as well factor that out and fill it in at the very end. We've got 6 times 10 to the negative 9. Also, everything's got coulombs and meters squared. So we'll pull that out also. That way we're just dealing with raw numbers.
Sorry,
go ahead.
Do we have to multiply K in for our answer, or can we just leave it as a variable?
It's often just left as a variable. If you want an actual numerical value of the force, like so many newtons, then you would actually fill in the value of K. But in many situations, we just leave the result in terms of something times K anyway.
Okay.
In this case, since it's asking for the magnitude, I think it is expecting you to fill in the value of K. But I would just leave K as an arbitrary constant until the very end and then fill it in. And also units of measurement that show up in everything can be pulled out as well. So I'm just going to write this as numbers and then coulombs per meter squared at the end. 0.1 squared is 0.01. And then 54 times 10 to the negative 9 over 0.04. In fact, we might want to pull out the 10 to the negative 9 also, because that also shows up in every term. That'll make the resulting numbers easier to work with. So now we just have 6 divided by 0.01, 54 divided by 0.04. 0.01 is also what fraction?
1 over 100.
Yeah. So 6 divided by 1 over 100 is 6 times 100. So we just get 600 plus, and then 0.04 is what fraction?
4 out of 100. So that's like 1 over 25. Wait,
yeah.
no. Wait, yeah.
Yeah, that should do it. So 54 divided by 1/25, that's the same as 54 times 25. And 25, actually, it might be more useful to write that as 100 over 4, because then we can divide 54 by 4. That's, wait, does that work out nicely? I guess 52 would be 13, so 13 and a half. So 54 over 4 is 13 and a half, times 100 would be 1350, I guess. Does that look right? For 54 over 0.04?
0.04. Yeah, 1,350.
Okay, sounds good. And then we add the 600 to that from the 6 over 0.01. And we get K times 1,950 times 10 to the negative 9 coulombs per meter squared. So that's the electric field. Any questions on that so far? So we've got the total electric field at location B, but location B isn't really just an empty point in space. What's actually at location B?
Charge?
Yeah. So if we actually investigate that charge now, we have this test charge and we know the electric field at that location. How do we convert electric field into the actual force on the test charge?
Do we multiply K out to get newtons?
Well, multiplying by the K will tell us the electric field. But how do you convert electric field into actual force? How are those related?
Oh, is it magnitude and then time? Oh, never mind. Yeah.
Yeah, we've got to multiply by the charge. In fact, you could generally think of electric field as, I generally think of electric field as the capability of the location in space to provide a force on a charged object. And specifically, if there is a charged object placed there, the electric force is the charge of that test object times the electric field at that location. We have the electric field at that location, including a times K, which we can fill the value in later. But we got to multiply that by the test charge if we want to find the force on that test charge. So let's fill that in. We've got electric force is the test charge, charge B, -6 times 10 to the -9 coulombs, times the electric field, which is K times 1,950 times 10 to the -9 coulomb per meter squared to the left. And I'm filling in to the left here because direction is important for vectors. And we do care about the direction of the final force. We're multiplying that vector to the left by a negative scalar. So what's going to happen to the vector?
It's going to flip.
Right. Which means we can now that we know that, we can ignore the negative sign here and just say the result is to the right. So filling this in, we can just multiply. We've got 6 times K times 1950. I'm just going to group together all the terms without the 10 to the -9. Times 10 to the -9 times another 10 to the -9. And to the -9. So 6 times K times 1,950 times 10 to the -9 times another 10 to the -9, and also a times K, I included that. And what do the units work out to here? If we combine the units we've already got.
Newtons?
Eventually they're going to be newtons, but I don't see newtons here yet. If we just combine coulombs from the charge times coulombs per meter squared, what does that give us? What's coulombs times coulombs?
Coulomb squared.
So coulomb squared, and then meter squared, nothing to do with that yet. So coulomb squared per meter squared, and that is that much to the right. And we could probably simplify this a bit. 6 times 1,950 would be 11,700 times K. And what's 10 to the -9 times 10 to the -9?
Is it
what do
negative?
you do with those exponents?
Is it 10 to the -18?
Yeah, we can just add the exponents because we're multiplying, and we still got coulomb squared per meter squared to the right. And at this point, I think that's all we can really do without filling in the value of K. So I would go ahead and fill in the value of K at this point. Do you have a value of K?
I think it's 9 to the power of 10, right?
9 times, wait, 10 to the, shoot, what was that again?
9 times 10 to the power of 9, right? It's like 9.
Let me double check that.